A small lecture briefly on K-mer coverage. So, why do we consider this K-mer coverage thing at all? Let's see if we can understand that. First of all, let's set some sort of notation here. We have sequenced the genome, and capital G is the length of the genome, number of positions, right? Imagine this setting. We have then sequenced with n reads, and the reads are all L bases long. They don't have to be the same length. We can replace this with the average, but for simplicity now, let's assume they all are same length. Read coverage, that's something we have seen before. Expected number of reads covering position I. So we just consider any actually random position of these capital G positions, and then the expected number of reads covering this is the read coverage. And this, of course, reflects how much we have sequenced, right? So larger N give a larger coverage, or a larger L gives a larger coverage. And here's the formula for it. D, that's the read coverage or depth, N times L divided by G. So we actually just sort of add up all the read lengths, divide by the genome length. That's the average or expected number of reads covering any given position. But it varies, of course. We have seen it's not like this is constant, right? Because it's random. The reads come from random positions. So some have more, some have less, but this is the expected value, the average. Note that reads covering position I are not identical to each other, and not at all, actually. Here we can think of a piece of a genome, right? This is the genome we are sequencing. And then, of course, reads are coming at random positions from this region now. There are, of course, many other reads, but let's only focus on this small region of the genome. And some reads come from here and here and there. They all cover, for instance, this position here, right? But when you put them up like this, it's not so easy to see that that these 5 reads come from the same region, because this is how we see the reads. We don't know the genome, right? So we can't really align them like we do here. This is how we get them in our data sets. So the whole sort of motivation for looking at K-mers now is to sort of discover. We can see here that there is a region here, right? All these reads share the same sort of K-mer here. There's a part of every read that is the same, but they are on different positions in the read. So the whole read itself, they are very different from each other, right? If you compare the whole reads, it's a part of this read that looks like a part of this read, looks like a part of this read, and these parts are the K-mers, right? That we are going hunting for now. So here I have sort of highlighted that there is a sort of something in common between these reads. So why K-mer coverage? Well, by looking for regions of length K, we can first of all count how often we find them in the reads. And notice we don't need any knowledge of the genome itself to do this. It's enough to have the reads. You can look up the K-mers in every read and count how often you see the various K-mers. And that is actually K-mer coverage. K-mers actually found in the genome should occur as often as suggested by this K-mer coverage. We will see that. So this is very important. There is a sort of we have an expected number of occurrences of each K-mer. And then if we see some K-mers occurring very few times compared to this expected value, this is probably due to sequencing error. So by looking at and counting these K-mers, we can actually detect sequencing errors. And that is really a motivation for doing this. Finding the errors in our reads. Wow. First of all, if we have a read of length L, this reed has L minus K plus 1 k-mers. This is always true. Why is this? Okay, here is the reed, and this time the reed, 17 bases long. Let's now look at 5 mers. K equals 5. And then, of course, the first 5 mer is here, the second one is here, the third one is here, and so on. And if we just keep on collecting them, we will see that together we collect now 17 minus 5 plus 1 equals 13 5 mers from this reed. Right? So even if the reed is 17 long, you can't collect 17 k-mers because the last k-mer can't start at the last position, right? Because then there is no, there isn't k, there aren't k bases left to fill up the k-mer. So we always have a little bit fewer k-mers than we have length of the reed. And the relation is exactly this one. So the reed coverage from before, we have seen this expected number of reeds covering a position I on the genome. The k-mer coverage is defined slightly different. It's also an expected number of reeds, but it contains the k-mer that starts in position I on the genome. So it's no longer enough for the reed to just cover this position. It must also contain the k-mer that starts in this position. And why should it start? Why not end? Well, it could. It's just a matter of choice how you define it. I define it as a k-mer starting in the position. But you can do exactly the same reasoning and say that the k-mer must end in position I, or the third base in the k-mer must be in position I. All these will give you exactly the same result at the end. So by saying that we only focus on k-mers that starts in a certain position, there's nothing special about that. Yeah, so not all reeds covering position I contains a k-mer that starts at I. Of course, we can imagine that from the previous slide, but let's have a look at it again. So this is the piece of the genome, right? Here is position I now, any random choice really, just. And then this is the region we are looking for, the k-mer that starts here, right? And which reeds are covering here? Well, this reed will cover I, right? The reed that starts in this position and comes from this region of the genome covers I, right? Also, this reed starts in the position before, also covers I. And this reed starts in 2 positions before, also covers I, and so on. And eventually you can see here we have a reed which is also covering position I, but it doesn't contain that k-mer because now you can see it's a little bit, it ends too soon here. So I changed the color slightly here. So these last few reeds that I list here in a slightly lighter color, they all cover position I, but they don't contain this k-mer because they end before the k-mer is found, you could say. And of course, we know that in total there are capital L different possible reeds that can cover this position. But we saw from previously that, okay, not all of these contain the k-mer, only L minus K plus 1 of them can cover I and at the same time also have this k-mer. So these down here are the ones who cover I but don't contain the k-mer. So fewer reeds contain the k-mer here. So the probability of a reed of length L covers position I, this we saw earlier, this is exactly this one, right? The total number of pink reeds in the previous slide is L. And since this is 1 out of G positions, the probability that any random reed will cover this position is L divided by G. So exactly the same reasoning we can now use. The probability that the read L contains the k-mer that starts at position I is now by just replacing the numerator here. Slightly fewer. L minus k plus 1 divided by g. There are still g different positions where k-mers can start, right? And now this is the number of reads that contain k-mers starting in a random position. When we computed read coverage like this, we said that the expected value here, the expected number of reads, is simply n times the probability. This is the binomial expected value, right? So this is the probability, right? And so this is sort of the probability of when you flip a coin, heads or tails, right? Two possible outcomes, either you cover or you don't cover. And if you do this coin flipping n times, this is the expected number of coverages. So this is the probability of coverage happening, you could say. This is how many reads you draw randomly, and then you get this number of expected coverages. Now we use exactly the same binomial reasoning and say that not read coverage, but k-mer coverage. I call it dk then, to indicate that this is not the read coverage. It's still a sort of a coverage or depth, but it's related to the k-mers. So we use exactly the same formula, but we just replace the probability. Instead of L by G, it's now this other probability, right? And then we can do some simple rearrangement here. We just multiply by L divided by L, which is 1, and that's of course legal. Any fraction you can multiply by 1, why not? And why do we do this? Because we now want to rearrange these two factors here. So notice I just flip their order, and that you can do because this is multiplications all the way, right? And now we notice that what is here is exactly the same as here. So we can actually replace this with D, the read coverage. So you see that k-mer coverage is simply read coverage multiplied by this. And this is always a number slightly less than 1. Because this here is always slightly less than this here, because we subtract k plus 1, right? So the k-mer coverage is always a little bit less than the read coverage. And the longer the k-mers, the smaller it gets, you could say. So this is the formula for k-mer coverage as a function of the read coverage. Okay, let's see how this k-mer coverage thing helps us detecting errors. Again, consider this the genome here, right? And we have some reads. But now notice this read here, also coming from this region. It has a sequencing error marked with the red here, because you can see that all the other reads have G in this position, but for some reason this particular read gets an error here, so it gets an A instead of a G. And this happens, right? This is sequencing errors. Some reads have some wrong base somewhere. So if we collect the reads like we normally do, right? We don't see the genome, right? Because then we wouldn't sequence if we knew the genome. So this is sort of an imaginary situation, right? Where we can see how where the reads sort of originally come from on the genome. But this information is hidden for us. This is what we have. And it's impossible here to see if a base is wrong or not by only looking at the reads like this. However, we can detect the errors if we see them in the proper context. So here we have again the reads, and let's now look at k-mer frequencies, the number of times we observe each unique k-mer. So actually start out by collecting all the k-mers you can find in all reads, and then count how often you see them. And the K-mer frequency specter is for each frequency, we count how many unique K-mers have this frequency. We will see that shortly. But let's focus on only a part of this here now, right? Where I put this frame. So inside this frame, count all the formers, right? And then it would look something like this. CGGT, this one here. CGGT, we see it 2, 3, 4, 5 times, right? Because 5 out of these reads contain this K-mer. So we get 5 occurrences. And the next K-mer starting here, GGTC, also 5 times. And the next one also 5, but then we can see this one, GTCA, coming here. GTCA. This is only once, right? Because the other 5, they are GTCG here. That's the one before, right? This one occurs 5, but this one once. And then you move to the next position and so on and so on. And notice now, these 3 K-mers here came out with very low frequency compared to the sort of normal outcome. The other 5 reads are without errors. They agree with each other, right? On how the K-mers should look like around this region. So they come out with, those K-mers come out with high frequencies, high counts. But the read that had an error stands out, delivering, you could say, these 3 K-mers that no other read has. And this is exactly how we detect errors. Unusually low frequencies of K-mers indicate that this is something unusual, right? And errors are unusual. Errors always make the read look different from all the other reads coming from that same region. So, if K-mers are long enough, I mean the K-mers we looked at now are too short, but if we make them longer, like 15, 20, 25 bases around that length, they should appear approximately 1 time in a genome. Even if genomes are big, they don't run by random chance. A read of a certain length will hardly occur more than once. A few exceptions we can accept, but in most cases, 1 occurrence in the genome, right? In the genome. So this means that when we go counting K-mer frequencies, we count how often each K-mer is seen in the reads. And since the reads cover the same regions, we expect to see the same K-mer over and over and over again. And how many times? Around this dk number of times, the read coverage. So these are the counts of the K-mers, and then we look at the frequencies, as we call them. We count how often we see the various counts. And that is what you see displayed here. So here you now see the frequencies, the K-mer frequencies, and on this axis you see the frequencies. So it means you go out and count the various K-mers. Some occur 30 times, some occur 40 times, some occur 50 times, 60, 70, right? And now we count how many K-mers occurred 50 times. That's this bar. How many occurred 60 times? That's this bar, right? How many occurred 40 times? This bar. So up here you have sort of the number of unique K-mers occurring a certain number of times. And then you can see this starts looking like a Poisson distribution or a binomial, and that's if there is sort of if all K-mers occur exactly 1 time in the genome, and all the randomness is due to noise, you could say, or there is no systematic component in it, then it should follow a Poisson distribution. And the expected value should be this dk value, the peak. the mean value in here, right? This is how often we expect to see k-meres in our reads. So k-meres with very low frequencies, and that means down here, occurring very few times, once or twice or something like that, they are probably due to sequencing errors. So if we have now a bar here with the many k-meres down here, it indicates k-meres coming from parts of reads where there are some sequencing error. Should also mention that k-meres from a repeated region that occurs C times should be seen C times dk time. So not so rarely, but quite often actually when we make a plot like this, if we actually do the k-mere counting, we will do that in an exercise and have a look. Actually do the k-mere counting of the reads. You will see one sort of major peak here at dk, and then you typically see another smaller peak at 2 times dk. Those are the regions of the genome that are repeated twice. And then you have an even smaller peak at 3 times dk. And so on. If you have, but they are quickly getting smaller, right? Because only smaller part of the genomes are repeated that many times. But the peak of this, the main peak, indicates the dk value, right? So actually we can directly from a histogram like this get a good estimate of this one. And notice from the formula, actually to compute it accurately, you need the size of the genome, G, right? The capital G. But actually, to get a reasonable estimate of this one, we can do that from here without knowing anything about the size of the genome. And then we can actually compute the size of the genome from this information by just using the formula and rearranging and solving for G instead of dk. And that's something we may do in an exercise. But okay, remember that the k-mere coverage is the peak, the major peak if you do k-mere counting of your reads. And that is an information we may need. And now we know that the read coverage is slightly larger, right? We can actually compute that from this one now, the read coverage, without knowing anything about the genome itself. And that's sort of fascinating. So counting k-meres is very useful for this and for other purposes.